Yeah, so we got some general information on sensation perception. Last module we talked about. So now we're going to start looking at some specific different types of sensation and the way that our bodies take that information in and then how it processes them in different ways. Okay? So, module 18, we're looking at vision specifically, so dealing with the eye. All right? So, basically, what we're talking about with vision are waves of light. All right? And we'll talk about the ear in another module, but sound are also in waves. Okay? So, they're waves of energy going through the air, and how your body interprets those waves depends on a couple things. So you have the wavelength, which is the distance from one crest to another of a wave. Okay, so this is the wavelength. So basically, it's the width, kind um, of the sound, and then we have amplitude, which is from the top to the bottom. Okay, so this is light and sound, and amplitude, which is top to bottom. Okay, so the how long basically it is. All right. So the way those work together is, and the process by which your body takes that basically meaningless, stimuli of just waves of energy flowing at you, um, and then puts that into some sort of meaningful data is called transduction. So the conversion of one form of energy to another. Okay, your entire sight is you just being bombarded by all these waves of energy, which, by the way, most you can't make any sense of. Everything outside of the light spectrum, your infrareds, your ultraviolets, or whatever, and above, like you can't see that. Some animals can, and so on, but humans cannot. So we only kind of make sense of this limited amount of stimuli that we receive. So, and we'll look at the exact process that happens in the eye that causes the transduction in just a second, but the conversion of one form of energy to another. All right. So the wavelength of the color, the sound creates, or I should say, the wavelength of the visual energy creates the color, or the pitch if it's for sound. The amplitude affects the brightness for light, and the loudness if it's a sound wave, and then the purity of it creates a saturation in color and the timbre for sound. Okay, so uh, the way that this is coming in from the sensation changes how you perceive it to be in your brain. Right, different wavelengths, purities, amplitudes will affect the exact color you're seeing or the exact sound that you're hearing. All right. So again, we have very limited transduction, being able to take this and make it meaningful. All of this stuff we can't see. We can't see those broadcast bands of energy flying through the sky. We can only see this limited amount of color here. All right. And you have ultraviolet and then infrared. All right. So parts of the eye. Okay, so here's the biology part of it. So you have a stimuli. I have a little candle over here sending light waves into your eye. First thing, you have the cornea here. So this is the outside of your eye. If you put on contacts, you're putting your contacts on the cornea. That's the outer covering of the eye. Okay. Then that light passes through your pupil right here, which is the dark part, which is the black part of your eye. That's just an opening. And then through your lens, which helps to focus it. All right, that's right behind there. Um, and then you have your cornea, your iris, which is the colored part of your eye. All right, so this is the muscle part, the colored part of your eye that basically contracts and expands depending on how much light. So you step outside in the morning and like a huge wave of brightness. You don't need all that brightness; it's too much. So your iris will contract, and it will like shrink up, like not allowed as much light through, like whoa, too much light. Versus it's really, really, really dark. You need more light to come into your eye for it to be able to see, and that iris is going to pull it up to dilate to open it up to allow more light in. All right, oops, sorry. Um, so light comes in, okay, through the front part of your eye. Then it goes to the back of your eye, and this is the business end. This is where the transduction is happening. Well, the transduction technically is happening in the brain, but that's where the information is actually being taken in by the body. All right. So your retina here is the back of your eye. This is where all the nerve receptors are. Okay. You have your rods, which are more on the peripheral part of the eye, and we'll talk about those more in a second. And then you have your fovea, which is the central point of focus, and this is where your cones are. All right. So it takes in all this information, and then it's sent through your optical nerve into your brain to make something meaningful out of. All right. And this is your blind spot. So the point where your optical nerve is, there's no actual receptors here. So this is actually a blind spot, and there's plenty of fun things you can do to find your blind spot. But there's no receptors here because this is where the nerve is going back into the actual brain. So there's nothing here to pick up, which mostly isn't a big deal because if it's a whole image, even though there's a hole in your vision, your brain can make sense of it and perceive, and you won't even notice it unless there's very specific things like the little dots on the paper that, you know, if you move it a certain way, you find your blind spot, it disappears. Your brain can't make sense of it because you just can't see it at all. But even if you saw half of the dot, your brain could then like make sense of the whole dot. Okay? So there's the functioning of the eye. Outside covering, right, goes through your pupil right here, goes through the lens, okay, to focus the images on the retina. Your iris controls how much light is getting through. It goes to, where is it, the retina, which has the different receptors on there. And the fovea is the central point of focus, and I can't get that thing to go away. But the optical nerve, okay, that's a blind spot where the optical nerve is, which takes the information back to your brain for perception. Okay, so your two receptor cells that receive light. You've got your cones and your rods. So your rods, much more numerous on the peripheral of your vision. Okay, detect black and whites, grays, much more sensitive and dim light. Okay, which is why when it's dark you can actually see really well on the sides, even more, better. It's not as affected nearly as much as your cones are because your rods can pick up on that dim light a lot easier. Okay, and then you got your cones, which are more of your fine details and color vision. All right, they work a lot better in well-lit daylight conditions, which is where humans usually operate, and that's your central point of focus in your fovea. So that's why, if you're looking at a color, you're aware, but as you kind of move away, it's really hard to see that color as much there. If you take that marker, that blue marker, and start it here, and then you probably won't be able to see the color until it gets much closer to your central point of vision, your fovea, which is where your cones are. All right, so the acuity is the sharpness of your vision. If you're nearsighted, okay, nearby objects can be seen more clearly. All right, and then if you're farsighted, you can see far things more clearly. All right, so if you're nearsighted, you can see up fine here, but if it's far away, it's hard to see. If you're farsighted, you can see down the street much better than maybe a book that's like right in your face. It can be hard to see. Okay, it just changes where basically your lens is focusing that visual data on your retina can change your ability to see. And obviously, we have glasses and stuff to compensate that for nowadays. All right. Some people suffer color blindness. All right, and there's a bunch of different types. Again, color blindness does not mean you can't see color. It means you can't perceive different types of color, distinguishing them from one another. There's different types. It's much more prominent in men because all you need is that because the XY chromosome, um, all you need is a carrier of it. Whereas if you're a female, you would need 100% of your genes to be the colorblind gene for you to actually have color blindness. So it's very much rarer in women than it is for men. Um, what happens for a lot of people, and now there are some techniques, there's glasses and stuff. You might be able to go on like YouTube and look up the videos of people like seeing color for the first time because the glasses can compensate for it. So color blindness might become a thing of the distant past. Technology is able to compensate, but it just means people. So the number 74 here, someone with this specific type of color blindness would not be able to see the number here. It just all kind of look the same and mesh together. So if you're looking at this and you can't see the 74 right here, well, you have color blindness to a degree. Okay, and there's lots of different tests for that. So how can we see color? Like what's like how is our brain able to interpret what we call color? All right. So a couple of different competing theories on that. So the trichromatic, that we have these three color receptors, that we have cones specifically for red, green, and blue, and those three color receptors together are able to form all the different colors that we perceive. Okay, so different cones seeing these different colors and bringing them together. That's the trichromatic theory. And then you have the visual processing theory, all right, which is stating that we have different kind of opponent processes for our retina. All right. So if you look at this flag, it's the British Union Jack. It's got the green, it's got the yellow. All right. Whereas the counter to that of green is red, and the counter of yellow is blue. So if you stare like this, what will basically happen is your retina will become tired. Okay, if you stare for about a minute, and then you look at another white object, like a background or something, this should appear as blue and red. It will if you do it correctly. So the basically the opposing processes, the on-off switch, allows us to pick up different colors. Okay, so the two theories, and then the combination of them together is the combined theory, where it's a combination of the two processes interacting that actually allows us to see the colors that we see and live our everyday world in. Okay, so the trichromatic theory and the opponent process theory are the two ones to know about. So we have our eyes; they take in light. It hits our retina and our cones and our rods. How does our brain make sense of it? All right. So how does the brain actually perceive? These are a bunch of just lines, flat lines drawn on a flat screen. But your brain still perceives it to be a three-dimensional figure that it's actually coming out of the screen. Looks like it's giving that illusion of it. All right. So how does that happen? This is where Gestalt psychology comes in. So Gestalt is creating a meaningful whole out of pieces from the information. So, for instance, okay, these are just a series of shapes. But when put together, you have this. Now, it's not a complete object. This is just a shape floating out, into nothingness. This is just kind of sticking out the back there. But what we can do is our brain can kind of close the loop. And close the loop there. And oh my gosh, now it's a panda. All right? This is just, shapes floating out in space, but our brains can put it together, fill in the gap. Here are the eyes, here's the nose, here's where the head is, and so on, okay? So, you've seen the Gestalt cubes where it's just the circles, just like a bunch of circles out there that have the lines in it, but your brain can fill in and create the cube out of what is missing. And oh my gosh, look at the enormous rat. It's huge. It's like half the size that he is. So this is like some 3-foot giant monster rat. Or is it just an optical illusion? Is it just the fact that it's closer to the camera creates the illusion that this actually much, much smaller little doll is a gigantic, huge oversized, ridiculous gift you would get for your girlfriend Valentine's Day or something. Okay? So what's going on? How does our brain take this light information and make something meaningful out of it? Well, there's a whole lot of different clues. Some of them binocular, using both eyes. So this relies on both eyes working together in conjunction. And some monocular. So this is just information gathering on either eye. Um, so the disparity between the two, the convergence, okay, you can focus on the object. Um, Distance based on either eye. So these are seeing how far away it is um, with both eyes and then a single eye. Okay. So there's a whole lot of processes that are going on that helps your brain to know, where the distance is something is away. Okay. And there's also consistency. Your brain knows. So for instance, different consistencies here. Um, so like you have a red ball and it's in the bright sunlight and you're taking it in and you take the red ball and put it in the shade, your brain understands that, like, oh my gosh, the color just magically changed and now it's a much 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 darker, almost black red. Like your brain still understands that it's red. As your dog is running towards you or something, your brain does not interpret that dog is growing in size. You have that size consistency, so your brain interprets it instead as getting closer. Okay, um, and then the shape. Okay, you're standing, and the door is like this. It's a rectangle, and they open it. Your brain doesn't perceive it as, oh my gosh, this door is magically changing shape and turning into a straight line. It understands that this door is opening toward you, and this part of the door is getting closer to your face. So your eyes work in conjunction sometimes. Sometimes the eyes work independently to understand distance away and size. But there are illusions there. Okay? So which line is bigger or which line is longer? Is it this one or is it this one? Actually, the lines are the exact same length. All right? Did you say that this one's longer? It's not. They're the exact same length. Which one is longer, this one or this one? Okay, again, looks like this one is slightly longer. Again, same length. Which line is longer, this one or this one? Same length, but the horizontal looks a lot longer. And then which cylinder here is bigger, this one or this one? They're both the actual same size. So there's different optical illusions that can fool the eyes into making something is longer or larger or whatever. But for the most part, especially in our actual experiences of the world, we're taking in constant. It's not just like this singular picture that's kind of messing with us, but we're taking in all this different stimuli. Our brains do actually a remarkably good job at understanding size, distance. I mean, it's the reason why we don't, walk into oncoming traffic, I guess, or whatever. But to understand, kind of where we are in relation with other things. All right. So that is vision for you. The process of transduction. Your eye takes in all the stimuli, puts it to your brain, and your brain is able to use all these different kind of clues to compile the meaningful perception of how you visually experience your day-to-day world. Okay, so next one we'll look at the ear and audio perception.